That is lecture 15. In that lecture, we discuss the use of diagonalization and some significance of rank. So use of diagonalization. What is the use of diagonalization? Diagonalization can be used to evaluate analytic function which instead of using variable they use matrix. So suppose we know that the diagonal is what, diagonal matrix is what, P inverse A P. P is what, model matrix. So this implies we can write a matrix is equal to P inverse D and P. Here D is what, diagonal matrix, and this P is what, this is a model matrix. And so now we can find, by the help of that we can find the function of that matrix. So what we do, we just write the matrix, model matrix, and then the diagonal matrix. You have to and then P inverse. You have to remember when we write the diagonal matrix, so we write not only the eigenvalue, we write the function of that eigenvalue in the diagonal, and just by the help of this we can find the function of the matrix. So we take an example here. Now take an example. For a matrix A, we have to find the exponential of A, that is e to the power A. So by use of diagonal matrix, we can find the exponential of A. How? So first we have to find the diagonal matrix. For that, first we find the characteristic equation, that is A minus lambda I determinant is equal to 0. That we get 1 minus lambda 6 2 2 minus lambda is equal to 0 0. Now after expanding that determinant, we get an quadratic equation, that is lambda square 3 lambda minus 10 is equal to 0. So we obtain a two eigenvalue, that is 5 and minus 2. Now we find the eigenvector corresponding to this eigenvalue. So the eigenvector, suppose we say x1 corresponding to lambda is equal to says minus 2. So we get a matrix, we write A plus 2I matrix, that is x1 is equal to 0. Now we get 3 6 2 4, and we just take x1 is what, x1 x2, that is an eigenvector corresponding to the eigenvalue lambda is equal to 2, and this is what, this is a homogeneous system. On solving that system, we get what, x1 is equal to minus 2k and x2 is equal to k. So we get an eigenvector, that is x1 is what, we get minus 2k k, or if you take k as a common, so we write minus 2 1. So this is an eigenvector we can take corresponding to the eigenvalue minus 2, and similarly we can find the eigenvector 6 x2 corresponding to lambda 2 is equal to 5. So as a similar process, we get x2, the eigenvector x2 is what, is 3 and 2. Now we have two eigenvectors x1 and x2. So now we write the model matrix. Model matrix is what, P is equal to, is what, the matrix which is obtained by the eigenvectors. So we write minus 2 1 3 and 2. So this is the model matrix. Now we find the inverse of that model matrix. So the P inverse is what, is 1 by 7 minus 2 1 3 2. So this is the inverse of model matrix, and this is the model matrix. Now, because we have to find the FA. FA is what? The exponential power of A. So we write P inverse, that is the inverse of model matrix, the diagonal matrix, and P. So here we write the inverse of the matrix, model matrix, that is minus 2, 3, 1, 2. Then the diagonal matrix, if you remember that, we have to write the diagonal matrix of that function. So we write f of a, that is the diagonal matrix. We have the two eigenvalues, that is 5 and minus 2, and the function is what? We have to find fa, that is e key power a. So we write e key power lambda 1 0 0 e key power lambda 2, and we write the model matrix, that is minus 2 3 1 2. Now after multiply these three matrices each other, we get 1 by 7 4 e key power minus 2 plus 3 e key power 5 minus 2 e key power minus 2 2 e key power 5 and minus 6 e key power, we get minus 2 plus 5 e key power 5 and 3 e key power minus 2 plus 4 e key power 5. So this is what? This is FA, means this is equal to e key power a. If we have a matrix A, then the exponential power of that matrix is what? This is the matrix. So by the help of diagonalization, we can easily find the power of the e power ax or such type of a functions. Some students are asking what's the significance of rank of matrix. So I explained in that video what's the rank or the significance of the rank of matrix. You know that a matrix is a collection of vectors. You can automatically imagine a vector as a point in a space. You just imagine that a vector is what? Is a point in a space. If you want, you can draw a line from origin to that point, put a little arrow on the tip. That is a vector. Now, normally we can imagine a two-dimensional or three-dimensional vectors. So we take a three-dimensional vector. So here you can see this is what you see a vector. Suppose this is a 7 3 5. This is a position of that vector. So you can imagine what? Yeah, the arrow, the 7 unit from the direction from the x-axis, 3 unit in the y direction, and 5 unit in the z direction. So this is a vector, as you know that. Imagine just of these three-dimensional vector. You can imagine adding these vectors by taking a tip of one and using it at origin from the other. That would be given some new vector, that is this one. So above that one, we add the origin vector. Suppose this is what? This is a, this purple line is what? 7 3 5, and this blue line is what? Minus 2 minus 1 and 5. So we got a new resultant vector is what? This is 5 2 10. So here you may notice that a new vector lies in the plane of original 2. It's no constant. So if we scale the original vector by some constant, we could shorten or increase the amount and point them in the opposite direction. However, they did still a point in the same direction when you add them, and they did still pick some new point on the same plane. So if we can say I scale our original vector, suppose 7 3 5 by 2. So the resulting is that my 3.5 1.5 2.5 through a new vector after addition, a different point, that is 1.5 6.5 and 7.5. It is still lies in the same plane. So if we divide by 2, so the vectors are lies on the same plane. Now you can imagine you took all possible combination of these two vectors, the set of all possible points you could reach by scaling and adding these two vectors, including the zero of each, is what is the entire plane that passes through a two vector and the origin. So when we do this, we imagine the space that vectors span. In this case, it's a plane. Imagine the two vectors we start with their actual point in the same direction, that one. So the 7, 3, 5 and 0.35 minus 3.5, 1 minus 1.5 minus 2.5 are two distinct vectors, but they point in the same direction. So no amount of combination these two would be ever escape and line they point lies on. Thus, we can say the space is spanned by two vectors in the same single line rather than a plane. So in each case, we had two vectors, but number of independent direction made the difference between the span plane versus a line. So the rank of matrix is what? Is a dimension of that space is spanned by the vector. So you can understand the rank of matrix is what? Is a dimension of that space is spanned by the vector in the